Welcome back. Today we're talking about applying properties of similar triangles, and one of the things that I want to show you is in this picture here. The use of perspective in art is really huge when we're talking about similarity, because if you'll notice, this little girl looks like she's putting her hand on top of this helicopter, but really it's because we're playing with the perspective, okay? And so this helicopter is really farther away, but it's smaller, and so it looks like that she's got her hand on top of it because she's in the foreground. A lot of artists use this kind of perspective to kind of create an effect when they're doing art. And so we're going to look at that later in this chapter, but that's one of the ways that we can use similarity. These are not necessarily triangles, but art is a way that we can incorporate similarity into the things that we're doing. Okay? And so what I want to look at is this lesson is about using the properties and specific theorems to try to find lengths in triangles. Okay, and so let's go down here and learn about the first theorem, the triangle proportionality theorem. If a line parallel to a side of a triangle intersects the two other sides, then it divides those sides proportionally. Okay, and so this triangle has a line that's parallel to one of the sides, and I've told you that EF is parallel to BC. So it divides the sides proportionally. The conclusion that we can make is this. Proportionality is about having two fractions. And so the fractions that I'm going to write here are fractions using these sides. Okay? And so the top part over the bottom part is equal to the top part over the bottom part. That's proportionality in this triangle here. Okay, and so this is going to be really useful because you know that we've seen a lot of triangles that look like this. Let's use that to find the segment length. Here's two examples. Okay, the second one that's highlighted is going to be for you, but let's try this first one first. If I want to find CY, I'm going to put a question mark there because that's what I'm going to find. Well, I notice I have a side that is parallel to a line that touches the other two sides of a triangle, and so I could set up my proportionality. Well, what I'm going to say when I set up my proportionality is I'm going to say 9, the top part of the triangle, over 4 is equal to the top part, 10, over my question mark. So 9 times what I don't know is equal to 40. Divide by 9. Divide by 9, and what I end up with is 4 4/9, because 9 goes into 44 times is 36. I've got 4 left over, so really this is 4.4 repeating. Okay, so that's a very simple way to solve for the length in a triangle. Let's see if you can try the next one. It's a little bit different because it's turned, but I think you can try this one, so bring that one to class when you come. Okay? Let's move on to the next theorem. Once again, it's okay to pause. Be a critical watcher of this video. It's theorem 742. Converse of the triangle proportionality theorem. If a line divides two sides of a triangle proportionally, then it's parallel to the two sides. So what I'm assuming here is that these sides already have this relationship, so I tested that. Well, the conclusion that I can make then is that line EF is parallel to side BC. Okay? And so that's what this sign is saying. That's what this theorem is saying. Test the sides, then the lines can be parallel. Okay? So we're going to verify that segments are parallel in example 2. We're going to verify that these sides are, or that these lines are parallel. And so I need to actually add this in. So I want to see if these two lines are parallel. So how am I going to do that? Well, I'm going to test the sides. So I'm going to say 42 over 21. And I'm going to put an equal sign and a question mark because that's what I'm testing. Is that equal to 30 over 15? Well, this reduces to 2 over 1. And is that equal to 2 over 1? Yes. So MN is parallel to KL. Simply test to see if the sides are proportional, then those lines must be parallel. Okay? See if you can try this next one. It's going to be a little bit trickier because I didn't necessarily put it in, but go ahead, you can write in these values. So AC is actually 36 and BC is 27. See what you can do with that. Bring that one to class. Okay? So these two things that we've so far discussed are really not too mind-blowing. They're really just dealing with proportionality as we've done it before and using those cross products to try to solve for a couple things. And what we're going to talk about today is the two transversal proportionality corollary. Now what we have here is we have two transversals, AE and BF, and we have three or more parallel lines dividing those things. It kind of looks like this. AB, CD, and EF are all parallel. Okay, and so that's what we're looking at here. The conclusion that we draw here, according to the corollary, is that if three or more parallel lines intersect two transversals, then they divide the transversals proportionally. And so what this gives us is AC over CE is equal to BD over DF. Okay, and so the pieces are now proportional because these lines are parallel and they're cutting transversals. Okay, we have an art application that goes with this. All right, and so let's look at this art example here. An artist used perspective to draw guidelines to help her sketch a row of parallel trees. She then checked the drawing by measuring the distances between the trees. Okay, and so these trees, pardon my lines, these trees are all representing these parallel lines. Well, we have three or more parallel lines that are cut by two transversals. Well, AD and KN are those transversals. Okay, and so what we are going to, AD and KN are those transversals that are cut by these multiple parallel lines. And so what we're going to check to see is, are these trees actually parallel? And so if we're going to find LN, let's see what we're actually comparing to. First of all, we need to know that AK is parallel to BL, is parallel to CM, is parallel to DN. So that's what we know right off the bat. And when we know that, what we're given is that then we have two transversals. Well, if we're finding LN, let's look at what we're finding, this piece here, we're going to test out certain things. And what we're able to say is KL over LN, so this top piece over this big piece is equal to, and we look over to the other transversal. Well, that's really going to be KL and AB corresponding, so AB over, and LN is this big piece, so this is going to be BD. I'm going to fill in what I know. Well, what I know is this. BD is actually equal to 1.4 plus 2.2, which is 3.6. And so when I fill this in, I end up with KL times BD is equal to LN times AB. Okay, that's the cross products property, remember? These get multiplied and these get multiplied. Okay, let's fill this in. Well, KL is 2.6, so 2.6 times BD. Well, BD, let me fill that in as well. Should have done that already. Probably confused you there. BD we have, because BD is that 3.6, so 2.6 times 3.6 is equal to what we don't know, that LN, times AB. Well, AB is 2.4. And so what I'm going to do is, then I'm going to step over here and I'm going to say divide by 2.4. And what we end up that being equal to is that LN is 3.9 centimeters. Okay? So we just need to work on seeing those transversals in those parallel lines so that we can use this theorem. Well, what I'm going to ask you to do is find LM and MN. So LM and MN. I'm going to give you a hint that you might need to use the fact that these three lines here are parallel, and the fact that BC is proportional to a couple of these different things. Okay? So go ahead and try that, and we'll go from there. All right.